We're studying IGCSE chemistry and we're starting reversible reactions and equilibrium C. In this class, we'll be looking at these three concepts about Haber process, contact process, uses of sulfur dioxide. That's the agenda. Sulfur dioxide, ammonia, etc. Pass through the question, obviously. Now, let's begin with the first thing, Haber process. Okay, what is the Haber process? We take nitrogen, N2 plus H2 to give us NH3. Okay, that's the first process we have. Now we need to know a few things about this process. The temperature at which it takes place, and what compromises are made when we do it. Now, can you see the notes here on the screen?
Yeah.
Okay, let's look at the syllabus booklet first. So the state symbols are quite important. You must put gas. Okay. Fine, that's done. Now, what else is there? You also have the sources which you need. Where do I get the nitrogen from? And where do I get the hydrogen from? Where do I get, that's it, actually. The nitrogen I get is from air. Hydrogen is from cracking of methane. Okay, let's see what's written. Yes, methane and air. Fine. These are the sources. Where do I get these reactants from, the chemicals from, to make ammonia? Now, what are we making? Haber process is the manufacture of ammonia. Haber process is the manufacture of ammonia, right? Now, after this, we also have, this thing, which we're supposed to do. Sulfur, we have sulfuric acid. Now, we made ammonia, right? Ammonia from here, which is NH3 gas. We got the sources as well. Now the conditions. Let's see. Can you read this out loud? State from here. Haber process.
A typical condition in the Haber's process has 450 degrees Celsius, 20,000 kilopascals, 200 atmospheric pressure, and an iron as a catalyst.
Now, so kilopascals or ATM, both are fine. We usually give the pressure in atmospheres. 1 ATM is 1,000 kilopascals. No, 100 kilopascals. 1 ATM is 100 kilopascals. That's the atmospheric pressure, which we all feel all around us. Now, when we say the conditions, we have to mention the temperature, the pressure, and the catalyst. Catalyst, what is a catalyst, Julia?
which speeds up the rate of reaction.
It speeds up rate of reaction without being
Any change to the reaction.
so without being changed. Okay, it does not change. Now the catalyst is the iron catalyst, and that's all you need to know here. Any questions? Iron catalyst. We don't say iron catalyst. It's actually iron powder. Okay. Yeah. Any doubts?
No.
Okay, so moving on with, let's see. Now, the Haber process is an exothermic reaction. Delta H negative. It's exothermic. If it's exothermic, then tell me, which temperature favors exothermic reactions?
Low temperatures.
Low temperatures. Exothermic is favored by low temp. Okay? Low temperature favors exothermic, right? But why are we using a high temperature then? Do you think 450 degrees Celsius is high or low?
It's high.
Very high, right? It's so high. So what should I do then? What do I do about this? Because the reaction is at a high temperature and I should be using a low temperature. Now, this is done because of certain reasons, and they will ask you this in the exam. Okay, this is your diagram. Okay. First, the nitrogen comes in, it gets compressed at the high pressure, and then it mixes with the iron catalyst beds. You can say iron beads, or here we say iron solid. And it cools down, and at the end we get ammonia. Fine. Now, why did we use a high temperature? That's the question. We used it because the rate of this reaction is very slow. Okay, the rate of reaction is very low. So because we want to increase the rate of reaction, we increase the temperature. Fine.
Yeah.
Let's read this part here. Let's take this whole thing to the whiteboard. So the industrial manufacture of ammonia, NH3, you add N2H3H2, get 2NH3, easy. Now look at this. Low temperature favors yield of NH3, right? This is what we know. Low temperatures favors exothermic reaction. Low temperature favors exothermic reaction. You can just put brackets, exothermic. Now, but high temperature increases rate of reaction. High temperature increases rate of reaction. So 450 degrees Celsius is chosen as a compromise. Okay? Any doubts?
No.
The reaction is too slow because reaction is too slow. Now you don't write this in the exam. This is what you need to write in the exam, which is given here. Basically, the reason behind it is that the reaction is too slow. Done. Now after this, you have one more thing. Let's see. You have the temperature, right? What about the pressure? Let's focus on the pressure now. So this is the reasons. Okay. Let's say the reasons for choosing these reactions, these conditions. Let's write it down. Reasons for conditions. That's for the temperature. Done. Now what is left? The pressure. Now tell me, are we using a high pressure or low pressure?
High.
High pressure. Okay, if we're using a high pressure, then that's not good for us because if I, okay, look, which side has more particles, left to right? Or which, actually,
Left.
different question. Which side has less particles?
Right.
Right has less particles, right? Okay, so it's the right which has less particles. And um, so if you increase the pressure, which side would be favored? Right or left? Low particle or high particle?
Right.
Right. So we know increasing pressure favors, increasing the pressure favors yield of NH3, okay? But the yield is already very high. No, but high pressure is expensive. High pressure is expensive, and the yield is very high, already very high. Okay. Any questions?
No.
So it's not economic to use. It's not economically viable to use a high pressure where the yield is already very high. Okay, and the pressure, the temperature, actually, the temperature should be low. But if you decrease the temperature, the reaction is so slow, then what's the use, right? So this is the
Yeah.
compromise. Okay, moving onwards. Okay, yeah. Wait. It's 200 atm. It's not a low pressure, is it?
No.
We made a small mistake. We're using 200 atm, okay? So we're actually, the yield is not high, okay? Just this much. That is a different reaction. Uh, we're using a 200 atmospheric pressure because we want to increase the yield. That's it. Okay?
Yeah.
So 200 atm is a compromise. For economic viability and safety. That's it. Write this in your notebook, tell me when you're done. Expensive and dangerous. For the catalyst, know that it just increases rate of reaction. Without being changed. If we use something other than iron, it might affect the reaction, and that could be a problem.
I'm done writing.
Then writing. Okay, perfect. Next one is your sulfuric acid production. the contact process. Now, before we move onwards, let's just see if we missed anything. No, we didn't miss anything. So you understand the reactions, why we chose them as well, right? And the sources. Clear?
Yeah.
Now what you need to study is about the contact process. Let's begin. What does the contact process tell us? This contact process tells us a lot of things, especially about the production of sulfuric acid, manufacture of sulfuric acid. Now, you know one is acid and ammonia. Is ammonia acid or base?
Basic.
That's basic. So they're teaching you in the syllabus to make one acid and one base, right? And that's like the background fundamental knowledge which everyone should have. Now, to make the contact process or to make sulfuric acid, you need 2SO3 plus O2. Make sure you don't forget the state symbol. Plus O2 gas gives us the 2SO3. No, wait. Okay, so this is not that simple actually. It's not as basic as this. Okay. Here it was very easy. There was a one-step process. In the contact process, it's not that simple. So we need to approach it properly. Wait. So what do I do here? We look at the first step, which is S plus O2 gives us SO2. Okay, we get sulfur dioxide. Then second process, you get 2SO2 plus O2 gives us 2SO3. This is your reversible reaction. The main reaction, this one. Then the third reaction is when you get the sulfur trioxide, you take it and you react it with 2S2O2, so H2S2O7 to get 2H2SO4. Wait, I think we're missing something. Write these down. This thing is called oleum. Oleum is H2 H2S2O7. That's correct. Yes, we don't take two of it. And 4. That would be wrong. Right, what we do is this. Okay, that's what you do. And then do this. Which gives you 2H2SO4. That's the correct answer. Okay, this is liquid, gas, liquid, liquid. Sure. This is liquid. Liquids are those which are not dissolved in water, right? And then once you dissolve it in water, you get aqueous. This is gas, sulfur dioxide, and oxygen, and then you get sulfur trioxide. Sulfur is solid, then gas, and then sulfur dioxide. Okay, so you have 4 reactions. Write them down, and then I'll explain each of them to you as well. Okay, done? Equilibria?
Yeah.
Now I'll just write what's happening in each of these steps. In the first step, you burn sulfur ore, okay, burn sulfur ore in air to get sulfur dioxide. So first you need sulfur dioxide. How do we get sulfur dioxide? By burning the ore, sulfur ore, which is solid sulfur in air. Then, next step, you react sulfur dioxide with oxygen to get sulfur trioxide. Most of it is written in the equation itself. Now, afterwards, you dissolve sulfur trioxide in H2SO4 instead of distilled water to get oleum. And finally, oleum is diluted using distilled water. Get sulfuric acid. Okay, so Javaria, read these steps from 1, 2, 3, and 4. What's happening?
Burn sulfur ore in air to get sulfur dioxide. Sulfur dioxide reacts with oxygen to give sulfur dioxide. Dissolve sulfur dioxide in sulfuric acid instead of distilled water to get oleum. Or the
Keep this.
oleum is diluted.
Yeah.
Okay. Oleum is diluted using distilled water to sulfuric acid.
To get sulfuric acid, right?
To get sulfuric acid.
Now, dissolve sulfuric acid in directly in distilled water to get or dissolving sulfuric acid directly. This is a key important point. Dissolving sulfur trioxide directly in distilled water gives acid mist. Okay, which is not good. That's the problem. That's why we don't directly put this in water, because the other reaction would be, or okay, SO3 plus H2O. Okay, that's all you need to do. SO3 plus H2O gives us H2SO4, and you're done. Why are we doing all of the extra steps? Do you understand? We need to do add this to this sulfuric acid, then get oleum. This is oleum, and then put
What is
oleum.
oleum again?
Oleum is this H2S2O7. It's like a compound which you get when you mix sulfur trioxide with sulfuric acid. So sulfur trioxide with sulfuric
Okay.
acid gives us oleum. Okay.
Yeah.
Now it's like indirect step. We could directly put sulfur trioxide into distilled water, not into sulfuric acid. And I would get sulfuric acid at the end, right? At the end. This is direct. But I can't do this because this would create an acid mist. Can you see it?
Yeah.
So if you directly just throw the acid into water, it would create an explosion of sort, a mist. Okay? Which is not good. It's very dangerous. So that's why we put it into sulfuric acid first. We have to get this from somewhere. Get this from somewhere, okay? Then get oleum and then put oleum into distilled water to get more sulfuric acid. Clear?
Yeah.
Okay. So this H2SO4 would be a gas here. Not really a gas, it would be aqueous, but a mist. Okay. We understood the steps which you need to take, the method. It's a bit more complicated compared to the Haber process, which was quite easy, right? Now, any doubts in this? Did you note everything down?
Can you show the written steps?
Which step?
The steps you wrote.
This one, method?
Yeah.
Okay.
Yeah, I'm done.
Okay, done. Now, 1 second. Okay, what do we do here? Now, a few things about the conditions, right? What conditions are these being carried out at? What conditions are these being carried out at? So, first thing first, the temperature, then the pressure, and then the catalyst. The pressure is going to be 450 degrees Celsius. Okay, same thing, is the same, 450. By coincidence, it's the same. Now, it's actually 2 atm, the pressure, and the catalyst is vanadium 5 oxide. Vanadium 5 oxide. You can't say vanadium oxide in the exam. This is important. Okay, mention it. Tell me when you're done. Finished?
Yeah.
Okay. Now, reasons for choosing these again. Same. Why did we choose these? system. Okay. Now, what you need to understand is the temperature. Okay. Again, it's an exothermic reaction. This reaction is the contact process, which is the main reaction here is this one. 2SO2 gas plus O2 gives us 2SO3 gas. And the delta H is also negative. Now, negative means it's exothermic. Same thing for this one, the exothermic. Again, Julia, are we using a high temperature or a low temperature here?
High temperature.
High temperature. Well, so the issue with this is, again, increasing the temperature could be good, okay, might be useful, but in reality, low temperature favors the yield of SO2. But okay, higher temperature increases rate of reaction. Same thing. So 450 degrees Celsius is chosen as a compromise. Any questions in this?
No.
So we're just choosing this because we want to increase the rate of reaction. If I get a lot of, okay, tell me, Julia, do you go to, let's say, some restaurant? Have you, I mean, maybe you've visited a restaurant recently, right? How long do you think usually, do you think it takes usually to order some food in minutes?
2 to 3 minutes.
2 to 3 minutes, okay? So 2 to 3 minutes. Is that how much it takes for your food to be prepared?
No.
How long does it take for the food to be prepared?
Around 10 to 15 minutes.
10 to 15 minutes to be prepared, right? Now imagine, okay, so what you also want high quality food, right?
Yeah.
You want the quality of the food to be high. You need high quality food. That's the time and the quality. Okay, high quality. Now the thing is, if I give you the highest quality in the world, right? Highest quality, but I take 17 hours. Would you sit in the restaurant and wait?
No.
No, that doesn't make any sense. That's absurd, isn't it?
Yeah.
But if I give you, let's say, okay, good quality, okay, good quality, but I take, let's say, around 20 minutes, would you sit in the restaurant and wait?
Yeah.
Yeah, so that's reasonable, right? The same thing goes for this here. If you want high quality, the quality is the yield, right? This is the yield. And the temperature, if I put the temperature at low temperature, I would get a very good yield, but the time would be very high. Okay, it would be very slow. Understood? Same thing.
Yeah.
That's the basic concept about choosing a compromise. You don't want the highest quality if you have to wait for 5 hours. Okay, that's the thing. Now let's move on. 1 second. Let's see. Okay, yeah, perfect. Perfect. Okay. The pressure. Now, is the pressure high or low here? Tell me, is the pressure high or low? 2 atm. That's very low. Okay.
Yeah.
So the as the yield is already high. So as the yield is already high, as in the quality is very good already, we don't need a high pressure. Okay. Any doubts?
No.
Now the last one, the catalyst. In the catalyst, we have, I think I told you, didn't I already? Rate of, yeah, vanadium 5 oxide, which is a solid. Solid, okay? Um, is it solid or gas? What do you think? It's solid, obviously. We have both of these are solid. It's important to know this, okay? Iron, obviously, we know is solid. Vanadium 5 oxide is also solid. We don't melt it. You will learn this in the future as well, that there are different types of catalysts. Some of them are solid, some of them are gas, okay? But here it is solid. That's it. Write it down, tell me when you're done. After you're done writing, read this part as well. Quickly, read the whole process quickly.
Sulfur is first burned in air, producing sulfur dioxide. It is then mixed with more air and passed over four separate beds of catalyst vanadium oxide at 450 degrees Celsius to form sulfur trioxide. It is then dissolved in concentrated sulfuric acid, forming a thick fumic liquid called oleum. It is then mixed carefully with water to form concentrated sulfuric acid.
Okay, so it's then mixed carefully to make the concentrated sulfuric acid. That's the important bit. Now, second, yeah, let's continue. That's done, right? So those were the two steps: contact process and Haber process. Just a few things you need to know before we wrap up the class. You should know about the uses of sulfuric acid, sulfur dioxide, and ammonia. Because why are we making sulfur dioxide? Why are we making sulfur trioxide? Why are we making ammonia? Each of these has its own uses. Let's write the uses here. Uses of ammonia. This will come in the exam, especially with fertilizers, okay? Uses are fertilizers, then explosives, then detergents. I think it should be enough, detergents, etc. Fine?
Yeah.
Let's just say pesticides and dyes. Dyes is more important. Dyes, textiles. I can give you infinite examples actually. This much should be enough. Let's just say pesticides as well. Okay, now for sulfuric acid. Now, when you actually solve past papers, okay, it will not be this simple. There's a wide variety of information which will be asked from you. They will ask you, why do we have sulfur dioxide in food? Or what does it have to do with phosphate fertilizers or glue, wood preservation, etc. So I'll give you some basic information now, and then we'll practice past papers in the next class. So sulfuric acid, use first fertilizers, okay? Explosives, same. Dyes, same. Okay, it's almost the same. Okay, you can say preservatives, wood preservatives. Okay, and then that's it. That's it, yeah. The main thing is this preservative, okay? Now, use of SO2, use of SO2 as a food preservative. Now, what is the answer for this? The question could be, why is SO2 used as a food preservative? Do you even understand what the word preservative means? Very.
No.
No, so we can't go forward, right? Let's see what preservative means first. Preservative is something which we put in the food, okay, to maintain its shelf life, maintain the shelf life. Let's see, look at this. Can you see these food?
Yeah.
Or if you look at, let's say, some juice, okay. When you go to a market, okay, you might see something like this. Can you see it here? Let's see.
Yeah.
Let's see. Is it contains permitted natural food color and naturally identical food colors? Okay. Preservative. Is the word preservative mentioned? I don't think it's mentioned. It says. Oh, it says no preservative. Oh, that's different. Okay. Wait. This is the wrong juice which we're looking at. This has no preservatives. We want a juice with preservatives. Regardless, if you look at the back, right, you will see something called permitted preservatives. Okay, that's what you need to see. Now, this allows us to save the food. Now, can you see this part where they're saying no added preservative?
Yeah.
Now, most juices have it. Okay, most food has it. Now, some research has shown that it's not good for your health. Okay, too much of this is not good for your health. But we do put it in most food where it is allowed. Okay. So why do we have it? Now we have it because it basically uh, it is a reducing agent. What is it?
Reducing agent.
Reducing agent. Now this reducing agent, it kills bacteria. That's it. Prevents growth of bacteria. That's it. Understood?
Yeah, right.
Any questions?
Yeah.
So SO2 is a reducing agent and it prevents growth of bacteria. That's it. So if you put this in any food and then you can leave it on the shelf, it will be okay. You can eat it. But otherwise it would be easily ruined. Okay, so that's the use of SO2, and that's the use of sulfuric acid, and that's the use of ammonia. Finished. Now, any questions? Tiberia? No questions, all right. Okay, recap. What did we study today?
The Haber's process and the contact process.
Haber process and the contact process. Any details you would remember from them? Anything important which you think?
The conditions.
The conditions are very important. All right, good. Now, the homework on this would be write it in the group again, and I will make sure you get the worksheet. You will also have the test coming in the next week, inshallah. So for that, the list will be given, but I want you to start preparing for this chapter. Prepare for this chapter because the chapter is almost over. This chapter and electrolysis and rates of reaction. Got it?
Yeah. Okay.
Write this in the group. That's all for today. Then take care. Goodbye.